Okay, so now in this lecture we will discuss about uh, procedural statement, uh, procedural assignment statement, the initial block, examples of initial block, some shortcuts in the declaration, the always block, and examples of always block. Now this procedural assignment, this assignment we use when we are writing behavioral style of modeling in Verilog. The procedural assignment is an assignment expression which assigns some value to a register type variable. So here procedural assignment means the assignment of some values or assignment of some expression to a register type variable. We already know that there are four register type variables: rig, integer, real, and time. So now procedural assignment means we are assigning some value or an expression to a register type variable, and this procedural assignment lies inside a procedural block. So always this procedural assignment statement you can find inside a procedural block. There are two types of procedural blocks. One is initial block and second is always block. Right? We already discussed these type of blocks in previous lecture also. So initial and always are the procedural blocks, and we can find these initial and always block inside the procedural um, uh, blocks, right? Okay. The left hand side of procedural statement can be, left hand side means suppose this is the some expression like A ampersand B, and this expression we want to assign to Y. So here the left hand side of the, so see, if this statement, if this statement is inside initial or always block, then the left hand side of this expression equal to, this is your left hand side and this is right hand side, right? So the left hand side procedural statement can be a variable of register type rig, integer, real, and time. So this Y can be a register type, integer type, real type, and time type. A bit select of these variables, example A within bracket 3. Suppose let us see, suppose we have declared some rig type, which is a vector of suppose 4 elements, 3 colon 0 Y, right? So here there are 4 elements of the Y are there. These are Y3, Y2, Y1, and y0, right? And let us assume we have declared another rig type, which is a scalar type, let us see x. So the meaning of this B part is the bit select of these variables can be means, for example, x, we want to assign to this x some value like y 3, right? So out of 4 elements of y, we are assigning only one element value, that is y3, to x, right? So this is possible, this can be done. C part, a part select of these variables. A part select of these variables means, let us assume we declared another rig type, and suppose these are one two element vector 1 colon 0 of m, right? So here what is possible, to this m we can assign y any two elements, right? For example 2 colon 1. If we write this, then what will happen, the two elements of y, these are y2 and y1, will be assigned to m. M already we declared a vector of two elements like m1 and m0, right? So to these two elements m1 and m0 we are assigning y2 and y1. So the part of particular vector can be assigned to the left hand side. Now this D point, a concatenation of any one of the above. So concatenation is also possible in the left hand side. See the example, S 2 colon 0 comma m2 comma p. So this is in the left hand side of equal to expression. So to these they will be concatenated now. What you will get after the concatenation? You will get S2 S1 and S0. These three elements you will get from this S2 colon 0, then M2, then here M2, and then P, right? So to this we are assigning a value of x plus y, right? So in the left hand side now how many elements in total we have? 1 2 3 4 5, total 5 elements we have, and these elements we got due to the concatenation, right? So this concatenation is also allowed in the left hand side of this expression. Okay. Now the right hand side expression can be of net type or register type variables, right? So here this right hand side. This right hand side can be net type or register type. It can be net type or register type, whereas left hand side expression can only be register type, right? So if we have any statement, any procedural assignment statement, then these are the few things which we shall remember, right? And procedural assignment we can find inside initial block and always block. Okay, another point is procedural assignments can only appear inside procedural blocks, initial and always. Just now I said the same thing. So procedural assignments we can find inside initial block and always block. Now two kinds of procedural blocks are supported in Verilog: the initial block and the always block. So already we said the same thing. Now initial block, it executed once at the beginning of simulation. So initial block execute only one time at the beginning of simulation, used only in test benches. So initial block is used only in the test benches, cannot be used in synthesis. Initial block cannot be used for the synthesis purpose, right? It can be used only for the simulation, and during the simulation to suppose there are some inputs. So what are the various inputs to that Verilog module, that we can give by writing the test bench. So for that we use the initial block, and during the simulation it will execute, it will run only once. Whereas always block, a continuous loop that never terminates. Always block runs continuously, right? It never terminates, it runs continuously. Okay. The procedural block defines a region of code containing sequential statements. So procedural block like initial or always, right? For example, initial, inside this we are having few statements, right? So these statements are sequential statements, right? So they will execute sequentially, the order in which they are written. So all the procedural blocks defines the sequential statements. So whether it is a initial block or it is always block, right? In both the cases the statements inside these procedural blocks are sequential in nature. So the region of code containing sequential statements, the statements execute in the order they are written, right? So the order in which they are written, so in the same order the statements are executed. Now we see this now initial block. So initial block is like this. It starts with the keyword initial, and if there is only one statement inside initial block, then there is no need of begin and end. But if there are more than one statements, then we have to write those statements inside begin and end. So here all statements inside an initial statement constitute an initial block, right? So all the statements inside initial statement, initial keyword is the initial block. Multiple statements are grouped using begin end. Same thing I said. The statements start at time 0 and execute only once. right? So the meaning of this statement is, so suppose our simulation starts at t is equal to 0, right? So at this time, at t is equal to 0, right, the statement starts executing. So whatever statements are there inside initial block, they execute at time t is equal to 0, and they execute only once, right? They will not execute continuously or repeatedly. Only once they will execute, and it execute at the start of the simulation time. If there are multiple initial blocks, all blocks will start to execute concurrently at times 0, right? So the meaning of this is, if suppose there are more than one initial block, right, then all the initial blocks execute concurrently at time t0, right? So let us assume, suppose there is this initial block, one initial block, right? There is this one initial block, and here we have some set of instructions: begin, end. Suppose this is initial block number 1, and let us assume there is another initial block. Suppose this is initial block number 2, right? It also has some set of instructions written inside begin and end. Right? So at time t is equal to 0, at the simulation time t is equal to 0, both the initial blocks will execute concurrently, parallelly, right? So if suppose there are 10 initial blocks, then all the 10 initial blocks will execute concurrently at t is equal to 0. Okay. The initial blocks is typically used to write test benches for simulation. It specifies the stimulus to be applied to the design under test, right? So suppose this Verilog code we have written, right? Let us assume for 2 input AND gate we have written some Verilog code, and underscore 2. Now it has one output, and let us assume it has 2 inputs, A and B, right? So this is our design under test or unit under test, right? This we are testing. So for this we have written one test bench, and various stimulus which are to be applied to this design under test, right? Stimulus means various values, right? For example, to A we want to give value 0 at 5 microsecond. We want to give value 1 at 10 microsecond, right? And for input B we want to give value 1 at 15 microsecond, right? So these values will be provided by the test bench, right? So test bench specifies the stimulus to be applied to the design under test. It specifies how the DUT output are to be displayed and handled, right? So output of this AND gate is displayed in the form of waveform, or it has to be stored somewhere. These things are mentioned in this initial block. Now example 1 for the initial block. Suppose we have written one test bench here. Uh, this test bench, okay, we have written for some half adder circuit, right? Now here you see we have written one initial block, right? Suppose this is initial block number 1, and in this initial block we mentioned since there are two statements, one is monitor, another is hash 5, a underscore tv is equal to 0, b underscore tv is equal to 0. So this is our stimulus, right? This is our stimulus. Right? These values are to be given to my input port of the half adder. Okay. So these two statements are written inside begin and end, right? Now in the same test bench I have written another initial block, right? This is my initial block number 2. Now here in initial block number 2, see this statement. This statement means after 10 unit time of the simulation, because here we mentioned hash 10. Hash 10 means after 10 unit time of the simulation. See, let us assume this is your simulation and here this is time 0 of the simulation, right? So when the time advances, suppose the unit for the time we are taking microsecond. So when the time advances to 5 microsecond, in that case, from the initial block number 1, here we have written hash 5. So hash 5 indicates at time 5 microsecond after the starting of the simulation, we have to assign a underscore tv 0 value and b underscore tv 1 value, right? So at this time we are assigning a underscore tv a value 0 and b underscore tv a value 1. Now with the initial block 2, here the statement is hash 10. Hash 10 means 10 microsecond after the start of the simulation. So here at 10 microsecond. So at this time we are assigning the value 1 to a underscore tv. At this time we are assigning 1 to a underscore tv and 0 to b underscore tv, right? Now we have written third initial block also. This is third initial block, and in this initial block this statement hash 5 hash 15. So this will assign the values to a underscore tb and b underscore tb at 15 microsecond after the start of the simulation. So at 15 microsecond, at this time at a underscore tv 1 and at b underscore tv 1, this value, right? Now we have written fourth initial block also. Now this initial block, what it will do, at 20 microsecond after the start of the simulation, means now at 20 microseconds, right? At 20 microsecond, what it will do, we have written $finish. It will stop the simulation. It will stop the simulation, right? So in this test bench we are having 4 initial blocks. All the initial blocks will execute at the same time at t is equal to 0, right? At t is equal to 0 they will execute. But in the initial block number 1 we have mentioned hash 5. So at 5 unit time, the values whatever assigned here in the initial block 1, those will be assigned to A underscore TV and B underscore TV. Now in initial block 2 also executed at the same time parallelly, right, at 0 time of the simulation. But since here we have mentioned the time hash 10, so at 10 microsecond it will assign the values of A underscore TV and B underscore TV, what is mentioned here. And statement number initial block 3 also executed at t is equal to 0. But since we have mentioned the time hash 15, so at 15 microsecond it is assigning the values A underscore TV is equal to 1 and B underscore TV is equal to 1. And initial block 4 it also executed at t is equal to 0, but here we mentioned hash 20, so at 20 microsecond it will stop the simulation. Okay. So here same thing is mentioned here. All the 4 initial blocks execute concurrently. The first block executes at t is equal to 0. The last block terminates the simulation at time t is equal to 20, right? Okay. This is example 2 of the initial block. So here also we have declared one test bench. Okay. So here there is an initial block and begin end, and between begin and we have written these statements, right? Okay. Right. So here in this case, in this initial block, it executes at t is equal to 0. These are the statement 1, assignment statement 2, 3 and 4. So this initial block executed at t is equal to 0, and once the simulation time advances to 5 unit time, means it reaches to this time 5. At this time the assignment of statement 1 will take place. Now, so all these are sequential statements. So first statement 1 executed. Once statement 1 executed, then statement 2 will be executed. Now statement 2 again we mentioned hash 5. So now after 5 unit time of statement 1, so here after 5 unit time means now from the beginning, if you calculate the time up to statement 1 5, and the second statement this executes at 10, right? So at 10 unit time it will assign the values which are given in statement 2 to A underscore TB and B underscore TB. Now in statement 3 again we have hash 5. So after 5 unit time of statement 2, so statement 2 was at 10 unit time, so statement 3 will be executed at 15 unit time. Then statement 4 is also having a time of hash 5. So this hash 5 means 5 unit time after the statement 3. Statement 3 executed at 15 unit time. So statement 4 will be executed at 20 unit time, and it will stop the simulation. Simulation will stop here, right? Okay. Now some shortcuts in the declaration. First, output and rig can be declared together in the same statement. For example, suppose we declared one output port, output Y, right? And we want to declare this as rig type also, right? Because maybe somewhere inside our procedural block we want to assign some value to y. So it is possible only if this y is rig type. If it is rig type, right? By first statement, a net is created. Y is a net type. By default, net type is created. Wire. But we have to declare it in rig type. So in the second statement, what we have done, rig y. We have declared y as rig type. So now we can assign the values to the y inside the procedural statement. Now in place of statement 1 and statement 2, we can write only one statement. And we can write in this way, output rig y, right? So here what is happening, y is declared as output port and the type is rig type now, right? So in place of statement 1 and 2 separately declaring it as output and then rig type, we can declare in one statement output rig y. Example 2, output 7:0 data, and we want to declare it rig type, so rig 7:0 data, right? So now in place of statement 1 and 2, we can write only one statement. And what is this? We can write output rig 7:0 data. So this is some shortcuts which you can use. Now a variable can be initialized when it is declared. So we can initialize the variable at the moment we declare it. For example, rig clock, we have declared clock as rig type, then we have written initial keyword, then clock is equal to 0. We are assigning the value to the clock 0. So now in place of statement 1 and 3, 1 and 2, 1 and 3 basically, 1 and 3, we can write only one statement, rig clock is equal to 0. So here we are declaring a clock as a rig type, and in the same statement we are initializing its value to 0. So this can be done, right? Okay. Now we will see always block. All behavioral statements inside an always statement constitute an always block, right? So all the statements, so this is the always keyword, inside this always keyword we have written these statements, right? So these statements which are inside the always keyword is your always block. Multiple statements are grouped using begin end. So same thing, just now we discussed in initial block also, we have to use begin and end if the number of these statements are more than 1. An always statement starts at time 0 and executes the statement inside always block repeatedly and never stops. So here what happens, this always block, it starts at time t is equal to 0, at the time t is equal to 0, and these statements which are inside this always block, right, they will be executed continuously, it never stops. Used to model a block activity that is repeated indefinitely in a digital circuit. So we have already written some Verilog codes also by using always block like this. Always @ then the sensitivity list, something we mentioned like A or B, right? And then we have written these statements. So what will happen? These statements are executed in a sequence. So always remember, all the statements inside the always block are sequential statement. Once the statements are executed, then the always block will be suspended and it will wait for event to occur on A or B, right? Event means any change in the value of A or B. So when the change in the value occurred on A or B, then again all the statements inside always block will be executed. After the execution of last statement, again the always block will be suspended. Then again it will wait for an event to occur on A and B. So again, if there is change in any value on A and B, again uh, all the statement inside always block will be executed. So always block is either active or suspended, but it never terminates, right? It never terminates. Okay, right. We can specify delays for simulation. So while writing these statements, if you want to show some delays during the simulation, so that delay we can mention in these statements. But but during the synthesis, those delays will be neglected by the synthesis tool. Okay, so here one example is taken: module clock underscore generating clock. One clock generator type of Verilog code is there. So here output rig clock rig by y, and then we have written one initial block, right? Inside the initial block there is one statement, and that is CLK is equal to 1 tick B 0. So here the meaning of 1 tick B, the meaning of this is means we are talking about B means bit type value, and that is only one value we are talking, right? There is only one bit value we are talking, right? And after this B we have written 0. This means the value of that bit type is 0, and this we are assigning to clock, right? We are assigning to clock. So with this statement what will happen? This 0 will be assigned to clock. If you want to assign 1 to the clock, then in place of this 0 you write 1, then 1 will be assigned to clock. So here this one tick B, this means 1 bit, right? And what is that bit? And that bit is 0, value 0, right? In this way we write the values. And after this initial block we have written always at the rate CLK hash 5 CLK is equal to negate clock. So what will happen? Initially the value of CLK is 0 due to the in the initial block. So you see here the value of CLK is 0. But this always block, this see always block and initial block, all these blocks they execute parallelly, concurrently. So always block this also executed exactly at the t is equal to 0. But what is the statement inside this block? Statement is hash 5 CLK is equal to negate CLK. So the meaning is this: after 5 unit time of the start of the always block, assign negate clock, right? So what is the value of clock at t is equal to 0? The value of clock at t is equal to 0 is 0 due to this statement, right? At 5 unit time after t is equal to 0, this statement is executed. And what is this? Negate clock. So negate clock means it will complement the value of clock. So earlier it was 0, now CLK will become 1, and that 1 will assign to CLK, right? So now you see here at this time, at 5 unit time, the value of CLK has become 1, right? Now after this, as I said, always block will never terminate. Again the same statement will be executed here, right? Because the value of CLK has been changed, right? Earlier CLK was 1, but now the value of CLK has been changed to earlier CLK was 0, but now the value of CLK has been changed to 1. So since the CLK value has been changed, so here CLK is inside the sensitivity list of this always block. So since the value of CLK is changed at 5 unit time, so again the statement inside always block will be executed. So now the statement negate CLK. Negate CLK means complement the value of CLK. Now the CLK is 1, so CLK will become now 0, and 0 is assigned to CLK. So now at 10, 0 will be assigned to CLK. So now previously CLK was 1, now CLK has become 0. So again the event occurred on CLK. So again this always block will be executed. So again this statement is executed, and now hash 5 CLK is equal to negate CLK. So again the value of CLK is complemented and assigned to CLK. So in this way we will get these type of block. And here there is third initial block, and here what we have written, hash 500 finish. So this block also executed at t is equal to 0, right? So at t is equal to 0 this block is executed, and the statement hash 500 means after 500 unit time stop the simulation. So when the time advances to, when the time reaches to 500 unit time, when it reaches to 500 unit time, at this time the simulation will stop. Simulation will stop. So here we are having two initial block, one always block. All these will execute concurrently. Initial blocks will execute only once, whereas always block will repeatedly execute it. Okay. So here initial and always blocks can coexist within the same Verilog module. So we can write the initial and always block inside the same Verilog module. They all execute concurrently. Initial block executes only once, always block executes repeatedly. Okay. Now a module can contain any number of always block. So it is not limited that you write only one always block. You can write any number of always block, all of which execute concurrently. Now for example, maybe suppose this is our hardware. This portion of the hardware we are writing by using, let us assume, always block number 1. Some other portion of the hardware we are writing by using some another always block number 2, and the remaining portion of the hardware we are writing by using another always block, right? So this is possible. So there can be any number of always block, but one thing, all these blocks will execute parallelly. Because see, in hardware what will happen, suppose some inputs are some value, some inputs are changing for this hardware and some inputs are changing for this hardware. So both should execute parallelly. It is not like that first this hardware will complete, then only we will start the execution of this. So this concurrency is a special feature of Verilog, whereas in high level language like C, this concurrency is not there, right? Only sequential statement is there. But here in always block, the statements inside always block are sequential, but always block in itself is a concurrent, right? Now the basic syntax of always block, always, so here this a we write in small, always at the rate event underscore expression. So that is the sensitivity list. When the always block will be activated, whenever there is event on the expression which is inside the this at the rate, right? Then begin sequential statement 1, sequential statement 2, like this, sequential statement n and end, right? So here this is end, small end. So only rig type variable can be assigned within initial block or always block. Already we discussed this already. Suppose this is equal to symbol, this is, here it is left hand side, right? So whatever value is evaluated at the right hand side, that value will be assigned to the left hand side, and this left hand side must be a rig type, right? Must be this register type, and mostly we have used rig type, right? Rig type is used in most of the cases. So in initial and always block, we assign the values to register type basically, but most of the cases we use rig type. Okay.